Good afternoon or good morning, whatever it is. And my appreciation to the organizers, of course, for making it possible to talk. I'm I'm an honorary member of the tribe of those dissatisfied with quantum mechanics. Not because it's complicated, not because it's weird. None of those things bother me at all. The only thing that disturbs me is that the interpretation is inconsistent. It's illogical, or in some cases the interpretations are so extravagant that I just find that they're concocted solutions to the real problem of the consistency of quantum mechanics. An example of that, of course, is the many world interpretations. In order to solve a problem with our little man-made theory, they suppose that the universe is made up of an infinite number of copies of the universe itself. This is a little bit too much. So over the years I've studied or searched out all the different types of interpretations that are available for quantum mechanics, and the one that I've settled on as the best possible candidate is so-called stochastic electrodynamics. It's a minority position. There are probably altogether in the world under 100 people who play with it at all, probably less than 20 who play with it seriously, but I happen to be one of the 20. Today I'm going to talk about the defects in quantum mechanics. I'm just going to mention them just to let you know in which direction I'm thinking. Then I'll describe stochastic electrodynamics in rough terms. Then the extension to stochastic electrodynamics is the specific version of it that I like best. Then some history of mathematical facts that pertain to all theories, in particular to this theory we're talking about now. And then the simulations that have been done, numerical simulations that have been done in recent decades to verify it, and then some conclusions. The first 5 categories are basically independent of each other, but whoops. Next. No, I'm going to go back to the whole thing, okay? I'm back on track here. Oh, that one goes back, okay. Now I should be able to go. Bam. How's that? Duality is, of course, one of the primary problems with quantum mechanics. It's ill-defined. The idea that something can be a particle and a wave when they have obviously disparate qualities and so on. Inventing a new term for it, wavical, is kind of a cheap way out. The philosophers don't like it. I don't like it. Many physicists seem to tolerate it out of desperation for coming up with something better. Another one, maybe worse, is entanglement. The very idea that you could have instantaneous communication of anything is defying common sense, logic, and mathematics, and relativity all at once. And yet today, that's one of the big topics in physics, huh? I mean, physics originally is the daughter of what the ancient Greeks called natural philosophy. The natural philosophers in ancient Greece really were concerned with the big questions in life: what happens when I die, who made the world, and so on and so forth. That particular enterprise, through history, evolved into 2 other enterprises. One of them is science, the other is theology. So we can now say today, physics is the sister of theology. And in many respects, they're very, very similar, especially sociologically, in terms of theories, among other things. So these are the features that have really motivated me to. Here's another feature that's very popular. It's been talked about already in our conference here today, yesterday, or the day before. The obscurities in quantum electrodynamics, especially in multi-particle systems, are profuse and profound. So, what are we going to do about it? Well, one thing is try to come up with a new theory. One of them, or a new interpretation, really. This is an interpretation. It's not a theory, it's an interpretation of a theory that exists and works very, very well. The fundamental assumption behind quantum electrodynamics, stochastic electrodynamics, is, you could say it turns quantum mechanics, conventional quantum mechanics, on its head. If we do conventional quantum mechanics and turn the crank, Eventually, we come to the conclusion that the free electromagnetic field has a foundation state, base state, ground state, with this kind of energy in it, as an energy density. That's a conclusion of quantum mechanics. Now here we're turning this upside down. We're assuming that we have a classical field with this energy distribution, and see what we can do with it. With this, and very simply, with the equation here, which is actually something that's straight out of elementary thermodynamics, we posit that a temperature field, which is T this is a temperature field, we have a distribution of the temperature field. It's comprised of the total field minus this one. And then that's it. But that there is no correlation between them, and so when you carry out these bracket averages, one term drops out there and you get this equation. This is stuff straight out of the thermodynamics book, elementary things. But that gives you a differential equation for which the solution is Planck's distribution. So Planck's distribution results without any assumptions whatsoever about anything being discrete, without any ladders of quantized values and so on, contrary to what Planck did. Planck did it the other way around and needed these discrete steps. In this case, with the stochastic electrodynamic basic assumption, get the Planck distribution for free, so to speak. So that can be taken as a clue, and you might want to ask what we can do with that clue. Well, the first thing you can say is, supposing we have some arbitrary particle bathed in this background, then just on dimensional grounds, one might define a frequency for that particle oscillating in a field that will be based on its mass, or you can go the other way around, say the mass is determined by the frequency with which it equilibrates. If any old oscillator is bathed in the field, it's going to speak back and forth, exchange energy back and forth, come into equilibrium back and forth with a mode in the field. The signals, the mode in the fields, will be coming from both directions, right? So some from the left, some from the right, with respect to any given arbitrary axis. If you add those two together, you're going to get a standing wave at the particle's position. Now, if you look at that standing wave in a frame that is moving with respect to the particle, or turn it the other way around, in a frame with the particle moving with respect to the frame, such as a frame with a slit in it, then those signals which the particle tunes to will be Lorentz transformed in such a way. Do such a thing. So what we have here is a carrier frequency modified by a modulation. When you look at this for a little bit, you see that the factors all come out such that the modulation is the de Broglie wavelength, and the carrier field is something that's typically the Zitterbewegung. So it says that the particles are being driven in Zitterbewegung by the background field, and the particle itself tunes just those frequencies in the background that have the modulation of the de Broglie wave in the frame of the slit. So the imagery here is that the particle going through two slits, say, actually surfs like a surfer on the waves in the background, goes through one of the slits, but the wave he's surfing on goes through two slits. So on the back side of the slit, once again, if he's going to surf on those waves, he's going to wind up stochastically being on a field, classical electromagnetic field, that diffracts at the slits, just as we know all classical electromagnetic fields do diffract. So with that, we've hit the jackpot actually, because this tells us that we can use this Fourier kernel, on the Liouville equation. And what happens is when you do that and do some cranking and turning, and not very much, pretty simple stuff in most cases, you wind up with the Schrodinger equation and its complex conjugate with a built-in interpretation, because you start with the Liouville equation. And that's what introduces the idea of stochastic and probabilistic wave function having the Bohr interpretation. But there's no magic in any of this. There's no, a Liouville equation doesn't describe any kind of particle that has instantaneous communication. It doesn't describe anything that's entangled or moves backwards in time or anything else. It's just a standard classical ensemble. It's governed by the Liouville equation. When you break it down into its components, you find that you have the Schrodinger equation regulating the probability density of particles which are bathed in the background. So, now I'm going to change speeds here, change gears a little bit, talk about some technical features of the Schrodinger equation. The Schrodinger equation at first blush looks like it's a diffusion equation because it has a single partial with respect to time. So far so good. The complication comes in, however, that that same term has a factor of I on it. And that factor of I turns out to be structurally equivalent to another partial with respect to t. And what that means is that the Schrodinger equation is not a diffusion equation. It is not a parabolic differential equation, partial differential equation. It is a hyperbolic differential equation, just like the wave equation. In fact, it is the wave equation, and that's why it has wave solutions that we all know all about. So, what that implies is that the solution space of this equation is a Hilbert space. This is not true of a parabolic differential equation. You can, in a Hilbert space, what you have are these Hilbert vectors, which are orthogonal to one another. In order to get different solutions of an equation orthogonal to each other, you need to have negative interference, right? You need to have destructive interference. The solutions to a parabolic equation won't do that. They won't, by themselves, do that. So only, I'm not sure about elliptic differential equations, whether they have Hilbert space structure or not. Just don't know offhand. But I do know that hyperbolic equations are the classical source of Hilbert spaces in the sense of functions. Hilbert space is actually a very general concept, and there are all kinds of things that are Hilbert spaces, if you look at it from a mathematician's point of view, that have nothing whatsoever to do with functions of any kind and so on. They just have to have these algebraic properties that are so nice and useful for doing Fourier analysis. And without a Hilbert space, you don't do this. You don't do any Fourier analysis. You need a hyperbolic differential equation most of the time. So anyway, the Schrodinger equation is a hyperbolic differential equation. Now, there's something very perplexing about the Fourier analysis. When Fourier first proposed doing this kind of thing, people said, baloney, this can't be work, this can't be right, it's got to be wrong. Because if you take a pulse in time and do the Fourier analysis on it, you'll get components that are finite from minus infinity time to plus infinity. That means we can sit here today and we should see components of pulses coming to us tomorrow. Can't believe that. So they negated it. And so the dispute went on, I understand, for 10, 15 years, when it was finally realized that the components of the Fourier series do not satisfy the initial boundary conditions of the equation itself. That if you have, the pulse does satisfy certain boundary conditions, the total pulse, but the components of the breakdown of the pulse individually do not satisfy the boundary conditions. Therefore, the components of the components per se by themselves do not constitute a solution of the problem which you're analyzing with Fourier analysis. Now, what does this have to do with physics? Well, This means that in the Fourier decomposition, that is, the deconstruction of the solutions of the Schrodinger equation in terms of eigenvectors, we get essentially what we're having there is the Fourier components of a physical solution. But they themselves cannot be a physical solution because they do not meet the boundary conditions of the equation itself. That means that all this fine structure that we have, all this outline of specific orbits for atoms and so on, cannot be physical. The physics in there, the physical solutions must be some kind of arbitrary whatever. But the gradations and so on that we think are not there, at least not when the atom is not in interaction with some measuring device. When the atom is in that kind of interaction, when you're measuring it, then the system ceases to be an atom and becomes the atom plus measuring device. And that may have altogether different solutions than the total solution. Okay, so how is this relevant? Well, it has to do with the idea that if stochastic electrodynamics is a good interpretation for quantum mechanics, then it ought to be possible to simulate the solutions that we know about in terms of diffraction and so on, in terms of diffusion and so on, and see if it works. Starting about 20 years ago, people have done this, and they've had a great deal of success with the ground state of hydrogen, but no success whatsoever with excited states. The problem tends to be that the electron, when they do the diffusions, when they do the simulations, tends to escape or impact the nucleus in short order, leading one to suspect that this can't be a physical solution, at least not if the simulation is accurate and honest with respect to the physics we know about that's incorporated into the simulations. This has led to kind of a stymied situation with respect to this SED interpretation of quantum mechanics, because people tend to say, well, this more or less knocks it out of the arena. If we can't do this, then it's probably not true. There's something wrong with it. My point, my main point here, the novelty in this particular presentation is actually that if you apply the same thinking to the solutions of the Schrodinger equation for atomic spectra that we just applied to the solutions of a pulse, that you would conclude that you shouldn't be able to simulate the pure eigenvectors in the Hilbert space of the solution. They are not physical solutions. They themselves do not meet the boundary conditions that we put on the total solution. So what's actually happening in the atom as it's there, of course, a statistical theory will never tell you in precise and bitsy detail what's going on. It will give you an average. The Liouville equation does not tell anybody anything about individual systems. It gives you a picture of what is possible in the phase space of the system in terms of the physical parameters that we do know. It's a statistical theory. It's not the final word. There must be somewhere, perhaps, a deeper theory that will tell us more. Whether we'll ever be able to calculate with it is another matter. So, that's the point I just made. Namely, I don't think we're entitled at all to conclude that the failure to simulate excited atomic states is an indication that this approach is somehow defective. In fact, I think it substantiates it sometimes. So, where are we? What's the fly in the ointment? That's it. This thing diverges. This says that at every little cubicle of space in the universe, there's an infinite amount of energy. Now, there's a couple of cute tricks you can try right away. You can try a cutoff, introduce a cutoff, but you find that if you make the cutoff high enough to include the frequencies that you need to explain atomic behavior, that it's 120 orders of magnitude too large, according to general relativity. That there would be so much space, so much energy at every little knuckle of space that the universe would have collapsed immediately after the Big Bang. And that didn't happen. So a cutoff isn't going to do it. You could put also some kind of killer factor in there, but that's then the same thing. You wind up with either too little energy at the part of the spectrum where you're doing ordinarily chemical quantum quantum mechanics or chemistry, or you wind up with much too much in terms of anything close to the considerations that one makes in general relativity. Now, my own view is that this is not a problem with quantum mechanics. This feature is probably a problem with electrodynamics. It stems from the idea that a field is a thing, and that the ground state of the quantized electromagnetic field is a thing. Or the fields at all are things. I think fields are not things. What fields are conceptions made to help us describe the interaction of particles. The particles are, I believe, the best candidate for the primitive inputs to logical theory. Back to the Greeks, they really would like to have discovered a means of certain knowledge, means of acquiring certain knowledge. They didn't want to be just working with guesswork and fantasizations and so on. Through the ages, that has come, that particular task has been taken up by formal logicians, who are most often associated with philosophy departments and not mathematical departments or not even physics departments. Formal logicians have studied the issue of how to acquire certain knowledge. And the state of play basically is that a so-called logical structure is certain knowledge. But a logical structure, of which the prototype is perhaps geometry or group theory, is comprised of basic elements, inputs, basic inputs with geometry as point, line, planes, and so on. And then some axioms, which are statements about the interrelations between these basic elements. And then when you have that, then you can get logical and construct syllogisms to deduce certain knowledge conditioned on the choice of primitive elements and axioms. But it's conditioned on the choice. And the fact of the matter is, though, that there's no logical way in the world to pick the logical elements. You're out in the blue. You're in the middle of the ocean and you've got to swim to shore and there's no way to get there. And a lot of people have discussed it, including Einstein, with respect to physics, and he pointed out you just have to kind of use your intuition and guess what they might be. And so nowadays we've guessed, but we haven't done it systematically, at least not in the textbooks. So we have a lot of concepts that can't be primitive objects that are taken as ontological entities. And one of them is field. Another one's energy. There's no such thing as energy. Energy is a bookkeeping concept. It tells you how much work, if I say such and such an object has so and so much kinetic energy, that number, kinetic energy, tells me how much work I have to do on that thing to capture it in my frame. But if somebody in a different frame would say it has a different amount of kinetic energy. That's a clue right there that it's not a thing. We can't discuss it as if we have a bucket of money or something. We don't think that's not a thing. Field, again, is also an abstraction, a complete abstraction. It's meant to say that the effect of one source of the field on a test particle for the field, which is sort of the mating particle to the field, will react in a certain way and so on. And on the basis of what you see the test particle do, you infer that the field was such and such at that point. But that inference does not justify the concept that there was a thing there. There was a contraption, but it's a mental contraption. All we can really say about the thing is that the interaction between these two particles was the key, or was the essence of what we're after. So what does that have to do with this? Well, in this case, this would be integrated over some little volume, right? If that volume happens to be somewhere in, say, intergalactic space, where there are no particles at all, then I would say there's no energy at all. You wouldn't see anything there until you put a test particle in there, which would react then with all the other particles in the universe. It makes sense. Electrodynamics, for example, the most basic and most understandable formula for electrodynamics is Gauss's formula. Now, there's no switch on Gauss's formula. It's always valid. So pick any two electrons, huh? One in my hair and one on the moon. Those electrons weren't created recently. They were created at the Big Bang, as it were, if there was such a thing. And they're going to persist until the Big Crunch, if there's going to be such a thing. And they've always been. The Gauss's formula for any arbitrary electron and any other arbitrary electron has been valid for all times and will be valid for all. So they've been in interaction all the time. So when you turn on your flashlight, you're not creating a wave, and there's nothing going from here to there. All we're doing is making the actions in the projector coherent, so that we can see a coherent response there. But actually, the electrons in here were in interaction, according to Gauss's law, with all the electrons in the wall forever, before we even built this guy. And this, what that means is that this is nonsense. This has no foundation in reality. The issue is not how much energy is in a volume in space, but rather how much energy is in all the interactions in the universe. And that would seem offhand to be finite, but substantial. So I believe this criticism is not really fatal. And that winds up my basic presentation. Question here right away?
Yeah, I want to ask, I think it's really applaudable that you bring logic back into the picture because...
I hope so, yeah. Thank you. Yeah. There's too much wildness in physics. There's free-for-all. Every day there's a new hyper idea, sci-fi ideas coming up. And loose talk about this and that. I think we got to turn the bolts tighter.
I think if we pay attention more to the language we're thinking, these
Another very
concepts, because logic is really a formal language, and I know that there are problems with it based on Gödel's theorem that you can't, whatever issues are involved with it, but at least we bring attention back to what we're thinking.
Well, Gödel's theorem says such things as, I think it's for number theory, there's no finite set of axioms that prove all the valid facts of number theory. That's pretty.
That's
I tend to think that number theory would be. I tend to think we're using number theory and arithmetic when we do calculations in physics. So if that's true of the calculations that we're doing in physics, then it's true of all of physics, which means there's no finite number of axioms that are going to ever solve all our physics problems. We better be a little bit more humble, huh?
And well, the last thing I want to ask is, the parabolic and the conic section of differential equations. I don't know what that property is called, where the elliptic, conic, elliptic, different.
There are three
of them, three cases.
Right.
Do they all satisfy, independent of the order, do they all satisfy the linearity principle? Is it, or are there some?
I think the answer is yes and no, but I don't know where the dividing line is.
Okay.
The main point that I'm making is that the most useful equation for quantum mechanics is a hyperbolic differential equation. Elliptic equations are also big deals and worth studying. That just connection with this thing.
Question all on the back. I'm sorry, we've got two people first. You third.
Very short question. You say how much energy, no? Your question. But I ask you, is finite or infinite energy? This is my question. You explain, you solved that how much you ask the question,
yes.
How much energy?
Yes.
But the question is, finite energy or infinite energy? Finite.
Well, it's according to the raw statement of the assumption, it would be infinite. But I think already that's when the original assumption that all fields are included at all frequencies is a formal deduction in quantum mechanics. And in this case, it's a hypothesis, so we're permitted to specify the hypothesis the way we'd like to have it. It's an input from the thinker. And so you can just rule out ridiculously high energy solutions that are not useful for doing quantum mechanics for chemistry. Quantum mechanics has been verified mostly at the chemistry level, right? Now we're trying to apply it, not me, but a lot of other folks are trying to apply it for the standard theory and particles and da-da-da-da. And if it works, they're great. That may mean we have to extend the range at which we're going to take these signals seriously. But it could be that it just drops out there. There's no signals in that range because we don't need it. The world doesn't need them.
I just want to make a comment, and then Cynthia, you carry on from there, doesn't need an answer. I'm carrying on from Sydney's comment about logic. Physics will not be disproved by experimentation. Physics will be disproved by logic thinking. You know, that if you have something that a new thought comes along, and you have a logic deduction which gives a logical conflict, which then would disprove a theory.
A physics theory will be proved by a quantum logic, but the application of any given, even logical theory may be disproved by empirical evidence. The evidence may be that the theory one has under consideration is not the theory that nature's using. And that it would disprove its applicability to what we're trying to do, but it may still be a logical structure.
You just might get it, wherever you're getting an inconsistency, whether it's in logic or number theory, you know that there's a clue there that something isn't.
Well, if it's logical, you've got the first case.
Okay, I love what you said about pulse versus sinusoid. I think that's exactly what Einstein did not pay enough attention to, probably didn't know, because it's the kind of thing you learn in engineering school rather than in physics school.
Well, Einstein did study engineering, so.
That's right. Many of the critics of Einstein have a background in engineering, and I think that that's what's wrong with special relativity theory.
Well, that came up, the point I tried to make there was at the time Fourier first proposed doing these series, that was an issue. I read that somewhere and I have not been able to find the story again. I don't know what happened, why that's the case.
So what's the issue?
The issue of the criticism of Fourier. When he first proposed doing these Fourier analysis, people said that the Fourier components are unreal, and therefore it's what
That's
you're
what
doing.
you're showing with that
That's what people said about Fourier. That's historic. I'm not going to comment on history of it. People said that the Fourier analysis is baloney because the components don't. It's not. You don't see a precursor of tomorrow's pulse today, ever. So he said, well, then obviously it's wrong. It looks like this, and especially in electrical engineering, electrical radar engineers and so on and so forth. They talk about Fourier components, and in their minds, these things are. I did some of this once upon a time. I worked at an office full of guys who did this, and while I was there, we thought in terms of the Fourier components of signals being real things, and it wasn't. They were solid, rock solid, good hard rocks, but they're not really.
So,
And the thing that is that the property you showed us going to infinity, is that what makes them not real? Did I understand that correctly?
Well, no, they're just not real because they don't, technically you would say because they don't satisfy the boundary
Boundary
conditions.
conditions.
Yeah, that's why they're technically wrong. Physically, they're wrong because they just don't exist.
When you say boundary conditions, do the boundary conditions have to be do they have to be formulated in terms of real numbers?
Well, yeah. The boundary, that's another big issue. It's a question of, as soon as you introduce delay, by the way, in mechanics, then no longer, then Cauchy type data that is on a film anywhere is sufficient. You then have to have an infinite amount of initial conditions. Basically what you have to have if you want to go to delay, once you put delay into the mechanical equations you're concerned with, you have to have a segment of the world line through some arbitrary light cone. And that's an infinite amount of energy. It's a different type of boundary condition from Cauchy boundary. That's another issue you should be aware of when you're reading about this analysis. Because as soon as you introduce relativity, you no longer can use, in most cases, maybe there's exceptions, but I'll say this is a generalization, you can no longer use Cauchy boundary conditions. You've got to jump out of that sandbox into one infinite amount. You need to have for the particles, if you're doing just particle dynamics. You've got to have the whirl lines of the particles between the past and future light cone with respect to some arbitrary point. Anything less than that, and it's arbitrary. The solutions become undefined.
Something that you said with your laser pointer, people talk about flow of energy from A to B. Well, it's not
Yeah.
in my view. It's there all the time.
Yeah. The velocity,
same amount
the
of
velocity, what's movement? You know, in order to say you have a velocity, it's like horse race, right? What do you need? For a horse race to get the horse has to have a nose. It crosses the starting line and crosses the finish line. Now, where in the hell is the nose on an electromagnetic signal? Especially since there's no switch on Gauss.
Yeah. The nominal.
So the velocity, maybe there's nothing moving, and it's just a ratio of energy and momentum transfer.
In principle, if you take particle physics and so on seriously, there's no actual finite velocity at all. There's only velocity of light, which isn't a velocity at all. So because all particles, like electrons, move at the velocity of light all the time, it's just that they zigzag in and out of vacuum and so on and appear to be slowed down. And if it's the velocity of light, it isn't a velocity at all, because that's just
Well, first of all, the light is actually part of this interaction, right? The interaction started in the Big Bang or wherever, and it's been going on all the time. It can keep going on. So you can't. There's no nose in the signal.
a lot of loose ways of
Start
talking.
line, finish line.
A lot of loose ways of talking.
Nose, the horse has no nose, or what is it? I know no nose, we know no nose.
The emperor has no clothes.
Another variation.
So, okay, can we think, we're going to do? Very good.